An 800-volt silicon carbide MOSFET dissipating 600 watts per square centimeter. Switching at 50 kHz. Cycling between -40 and +150 degrees Celsius across 250,000 kilometers of EV driving. The ceramic substrate underneath has to take all of it. For 10 years, without cracking, without delamination, without losing dielectric isolation. Across every major EV inverter platform, the answer is silicon nitride. 5 features anchor silicon nitride substrate duty inside silicon carbide power modules. First, flexural strength at or above 600 megapascals. This is what resists cracking under solder reflow temperature spikes and during the -40 to +150 thermal cycling that every EV inverter module endures. Second, thermal conductivity between 75 and 90 watts per meter per Kelvin. The high conductivity grade lifts the heat from a 600 watt per square centimeter silicon carbide die down to the cold plate without the junction to case bottleneck that limits alumina substrates. Third, dielectric strength at or above 15 kilovolts per millimeter. This is what enables thinner substrates inside 800-volt traction inverters while preserving creepage and clearance margins to automotive functional safety standards. Fourth, coefficient of thermal expansion at 2.9 to 3.2 micrometries per meter per Kelvin. The match with silicon carbide at 4 and silicon at 3 is what stops solder fatigue, copper layer delamination, and warpage across hundreds of thousands of power cycles. And fifth, thickness tolerance held to plus or minus 0.05 millimeters on full panels. The dimensional precision that delivers consistent copper wetting in AMB and DBC brazing, frame after frame, panel after panel. 3 sintering routes produce 3 property profiles, each tuned to a different power module duty. Gas pressure sintered silicon nitride, density 3.2, flexural strength 700 megapascals, thermal conductivity 20 watts per meter per Kelvin, covers the cost-sensitive inverter and industrial drive segment. Hot-pressed silicon nitride, density 3.3, flexural strength reaching 900 megapascals, thermal shock resistance to 800 degrees delta T, covers the toughness critical military and aerospace power conversion segment. The high thermal conductivity grade, density 3.25, flexural strength 600 to 800 megapascals, conductivity 80 to 100 watts per meter per Kelvin, is the grade engineered specifically for silicon carbide and IGBT power modules where junction-to-case thermal resistance dominates module sizing. All 3 grades share the same silicon nitride matrix chemistry. Silicon-bonded nitrogen, sintering aids tuned to the densification route, fracture toughness in the 5 to 8 megapascal root meter range, working temperature ceiling between 1100 and 1300 degrees. Standard rectangular substrate dimensions cover 10 by 10 mm at the small sample end through 190 by 138 mm at the panel scale. Standard round substrates span 5 mm through 150 mm diameter. Thickness ranges from 0. to 5 mm for thin high-voltage isolation through 9 mm for heavy-load structural substrates. Beyond standard catalog formats, 6 custom dimensions are reviewed against the design drawing. First, dimensions and thickness. With thickness tolerance held to plus or minus 0.03 mm on small pieces and plus or minus 0.05 mm on full panels. Second, flatness and warpage, controlled to 30 to 50 micrometries across a 100 by 100 mm footprint. Third, edge and geometry features, including chamfers from 0.2 to 0.5 mm, fiducial marks, alignment holes, and stress relief slots. Fourth, laser cutting and profiling for outlines, vias, cavities, and narrow slot features with controlled heat-affected zone. Fifth, Copper and metallization for AMB and DBC paths, with copper thickness at 0.3, 0.4, or 0.6 mm and pattern alignment tolerance reviewed against the module layout. And sixth, surface finish, ranging from lapped or fine ground bare ceramic at ARA 0.2 to 0.8 micrometries, through nickel and aurum plating and silver finish for wire bonding or solder paste application. Inside an 800-volt EV traction inverter, the silicon nitride substrate is the AMB or DBC base layer underneath 6 to 12 silicon carbide MOSFET dies. SiC engineering features make silicon nitride the industry standard for this duty. High thermal conductivity. The 90 watt per meter per Kelvin grade lifts the silicon carbide die heat down to the cold plate without the junction to case bottleneck that limits alumina substrates. Thermal cycling reliability. The 600 plus megapascal flexural strength resists cracking through 100,000 plus cycles between -40 and +150 degrees Celsius. High dielectric strength, 15 plus kilovolts per millimeter, supports thinner substrates without compromising 800 volt creepage and clearance. CTE matched to silicon carbide. 3.0 micrometries per meter per Kelvin minimizes solder fatigue and copper delamination over the inverter's 10-year service life. Mechanical reliability. Fracture toughness up to 8 megapascal root meter survives vibration and copper stress loading where aluminum nitride substrates crack. Flatness consistency. 30 to 50 micrometry warpage control across 100 by 100 mm panels delivers the brazing and bonding consistency required for automotive functional safety reliability targets. Together, these features make silicon nitride substrates the standard AMB or DBC base for every major EV inverter platform. Tesla, BYD, Bosch, Denso, Vitesco, Hitachi Astemo, and the natural choice as 800-volt silicon carbide traction architecture scales across the global EV transition.